We are glad to have Professor Badri Krishnan giving a set of lectures on theoretical aspects of black holes at the school. Before I hand over to Professor Krishnan, let me say a few words about him. He had completed his MSc in physics from IIT Kanpur in 1997. Thereafter, he had gone to complete his PhD at the Pennsylvania State University in 2002, after which he was a postdoctoral fellow at the Max Planck Institute at Potsdam, and he was later a group leader on astrophysical relativity at the Max Planck Institute, Potsdam. Then he moved on to the Max Planck Institute at Hanover, where he was a senior scientist, and he was there until 2020, it says. Okay. And in 2021, he moved to the Radboud University in the Netherlands to join as a professor. Professor Badri Krishnan has worked on various aspects of general relativity, gravitational waves, black holes, and relativistic astrophysics. And as I mentioned, he'll be giving a set of 3 lectures on theoretical aspects of black holes at the school. Over to you, Badri.
Okay, thank you very much for the kind introduction and for the invitation. So in these 3 lectures, I'll be talking about what are called quasi-local black hole horizons. And in the first 1 or 2 lectures, I'll do mostly theoretical work. And in the last lecture, I'll talk about some numerical relativity applications and also things from gravitational waves. And I should say that, by the way, do you have these lectures all the way for 90 minutes, or is there a break in the middle for?
No, we will go on for 90 minutes. Maybe you can stop once every 30 minutes to check whether there are questions, students have questions. If the students either raise their hands or left a question in the chat, I can read them out to you.
Yes, so I would say the students should ask questions at any time they want. So I'm not going to stop just for that, but I will stop sort of to ask questions at suitable times in the talk.
Sure, sure. Thank you.
You should really feel free to ask questions. Otherwise, it's more useful if you ask questions. That's an interaction. Otherwise, I don't know how much you've understood and how much is useful or not. So please ask questions, okay?
Thank you.
Okay, good. So let's start. So the plan for today is that I want to cover the basics of isolated horizons. But to do that, I need to first motivate the subject, and that will be the first half of the talk. So let me start with this figure that I'm sure that you've seen already in perhaps in Eric Gorgolon's lectures. So this is the Schwarzschild spacetime, and this is the Penrose diagram for that. And you can see my mouse cursor, right?
Yes, we can.
Okay, great. So we have the region 1, which is the exterior part of the spacetime, and that is the region where Riemannian observers live. This is then the black hole horizon at r equal to 2m, and the interior part is inside the black hole, and this is the singularity. And we have also, of course, these other 2 portions. This is the white hole portion, and this is the other asymptotic end of the universe. And again, as you must have learned in some of the other lectures, the surface r equal to 2m is a very special surface. So that is the event horizon. So that is the boundary of the causal past of null infinity, of future null infinity, right? So you take this surface here, that is future null infinity. So that is the endpoint of future outgoing null geodesics. You take the past of that, then you get this region here, and this is the boundary of that causal past, right? So that is then the event horizon. Good. So now this is the way that traditionally black hole horizons are defined, which is using event horizons. So the idea is that anybody inside the black hole region cannot communicate to anybody outside because of exactly the way that this horizon is defined. So then we have essentially a region of the space-time that's inaccessible to outside observers, and the boundary of this is then the event horizon. Okay? And there's other parts to this diagram which you don't really need. This is just simple aspect, which I'm sure you've seen before. Okay? If not, then you can ask a question already at this point. But let's go on. The important point is that event horizons have been used in all the key classic investigations in black hole physics. And I'll mention here the area increase law, the black hole thermodynamics, uniqueness theorems, black hole perturbation theory that you learn about in Eric Poisson's lectures. Then we have other aspects of things like topological censorship regarding topology of the black holes, and a bunch of things astrophysics, right? So then the question is, well, we have all of these seminal results in black hole physics and using event horizons. Sorry, just give me a second. Right, so the question is, do we actually need to go beyond event horizons? So why don't we just work with event horizons and be done with it? After all, it is useful and it is used to prove all of these seminal results in black hole physics. So why do we need to go beyond that? So to do that, so I'll spend a lot of time trying to motivate this. So the first point is, let's talk about the nature of a black hole horizon. So as you know, black holes grow as they swallow matter and radiation. So things, classically speaking, black holes can never become smaller. So as stuff falls into the black hole, it grows. So it could be radiation, it could be matter fields, it could be all kinds of things happening near a black hole, which causes this. And yeah, so they grow. And this is interpreted as saying that, well, this is what causes the area of the black hole to increase. And this leads then to the black hole area increase law, which I will describe in more detail. In short, it says that the area of a black hole can never decrease, and this assumes a suitable energy condition and cosmic censorship. So in fact, let's summarize a proof of this statement for event horizons. I won't go into too much detail, but at least enough to give you the main point. And by the way, let me ask, so you have done this in maybe Eric Gorgolon's lecture, right? So the area increase law. Could any students please confirm that?
Can students speak up? Can some of you speak up, please? Sajjad Ahmed says yes. Lakshman says Said. Yeah,
Okay,
they've said, yeah.
So I'll summarize a proof with the assumption that you've seen it before. So this will hopefully make sense. If not, then please ask questions. So to do this, let me start by defining what are known as the optical scalars. So for this, you have to imagine a congruence of null geodesics. So imagine a little bundle of light rays and look at the cross section of this light rays. And that turns out to be a two-dimensional space. Okay, so think of then a little circle of light rays and imagine this little circle as it evolves in time. So the circle can evolve in essentially these three different ways. The first is uniform expansion. So this is what is then called the expansion, and that is the expansion itself is defined as connected to the rate of increase of the area of this cross section. Then you have the other transformation that preserve the area, but this could be either a shear or could be a twist. So these are the other two transformations here. So this should be again be familiar to people who understand gravitational waves. So the shearing effect, and the last one is a twist effect that in fact we will not need so much in this talk. So in a little bit more detail, so if L is, you call L to be the null geodesic, and you say that Q is the two metric on the cross sections of this congruence, then the expansion is the trace of this quantity here, which is this covariant derivative of L. Okay, so take this and you contract this with the relevant two metric, and then this gives the expansion. So sigma is the shear, is the symmetric trace-free part of this tensor that gives you these transformations, and omega is the antisymmetric part, so that gives you these transformations here. Okay. So now what you need to know is that on an event horizon, look at the null generators of the event horizon, then you have to show that this expansion can never be negative, right? So because the expansion is connected to the rate of area increase, so if you show that this expansion is always positive, then you're done. Then you know that the area always has to increase. So let's see how would you do that. So the starting point is what is known as the Raychaudhuri equation, and I'm sure that Eric must have covered this in quite a bit of detail. So this tells you that the rate of change of the expansion, so again, assume that the geodesics are finely parametrized. So the rate of change of theta is given by this expression here. And you notice that every term is negative. So the first term is manifestly negative. So this one is also negative. Well, it could be zero, but it cannot be positive. So this is one term that we have to worry about because it's a positive sign here. And the last term is connected to the stress energy tensor. And that is, yeah, so that's also, the term itself is negative, assuming in a suitable energy condition. So the only thing to show is that, well, is this term, what happens with this term? And it turns out this null geodesic, in fact, is surface orthogonal, which means that you can integrate this null geodesic to get a smooth surface. And that implies that, in fact, that this twist must be zero. So this term vanishes. So therefore, theta dot always has to be negative. And in fact, it has to be smaller than 1/2 of theta squared. Okay. So that means, and this is something that you can really check in just one simple line of algebra, is that if theta happens to be negative at any point, then theta will go to negative infinity within a finite time. Okay. So it means, again, this does not necessarily mean anything is wrong with the horizon. It just means the light rays converge. And this is something that many of you see in optics all the time, right? So every time you see a lens or you see convergence of light rays, so the same effect here. So you have a point where the light rays are all focusing. And what it means is that if at any time theta happens to be negative, then it is inevitable that there must be a focusing point sometime in the future within a finite time. Okay. So then the next part of the proof is to show that, well, if there's a focusing point, then something else goes wrong. So therefore, there cannot be a focusing point, and therefore theta can never be negative. Okay. So therefore, theta must be positive or at least zero. That means that the area can never decrease, right? So that's a line of argument here. So how do we show that theta can never, there can be no focusing point? And I'm not going to discuss this in too much detail. I hope that this has been discussed in some of the other lectures. You can discuss this in further detail here if people have questions. But the basic point to remember is the following. Imagine first just, let's say, think of a Riemannian space. So just a positive definite metric, and think of a focusing point for geodesic. These are called conjugate points in this context. So the important point is that you know that geodesics will minimize a proper distance between 2 points, right, in the Riemannian manifold. But this is not true beyond a focusing point. So if you take sort of 2 points which lie on different sides of a focusing point, then geodesics do not minimize the proper distance, and that's in that situation. And the same thing is true in Lorentzian manifold in that, for example, if you have time-like geodesics, then beyond a focusing point, the proper time is not maximized. Okay. Similarly, for null geodesics, you don't have the notions of, because the proper distance is zero, of course, so therefore there's no notion of proper distance or proper time, but instead what you have is a notion of promptness, which means that if you look at 2 points and you say that, well, look at the first null geodesic that reaches from point A to point B, if there's a focusing point in between, then it means that there must be another causal curve which goes a little bit before point B. So this, when applied to an event horizon, means that, in fact, if there is a focusing point, then you can draw a causal curve from the event horizon to some point outside it, right? So it means that you can have a causal connection between the event horizon on the event horizon to point outside the event horizon, okay? So that cannot happen, and therefore you say that, well, theta can never be negative. So therefore theta must be positive or zero everywhere on the horizon. And therefore this means that the area increase law follows. Okay. So is this argument clear? So there's a very subtle argument. So I hope that this is clear to students. If not, then please ask questions, of course.
Are there any questions, students? Or raise your hand or leave a message in the chat as is convenient for you. There are no questions, sir.
Okay.
Okay,
so
there is one comment. I'm sorry.
Yeah.
There is a request saying, can you explain this again?
Okay, so this is where I wish I had a blackboard. If there is a blackboard here, maybe I can use it. Okay, let's try it out, right? So let's see if this works.
The question, Badri, is why can't there be a focusing point on the horizon?
Right, exactly. So this is what I want to show. So can you see the blackboard here?
Yes, we can. We
Okay,
can.
good. So imagine that this is the, let's say this is the event horizon. Let's draw this as a null surface here. So imagine a point A and a point B here. Okay. So if there's a focusing point in between, so the claim is that if there is a focusing point, then there must be a curve from A to B, which is causal, and which sort of reaches the location of B a little bit before B. There must be a curve like this. Okay. So I'm not proving this for you, but this is the same, a very similar argument to what is done for, let's say, a space like geodesic in the Riemannian space, right? So, so imagine now in the Riemannian space, if I have again a point A and a point B, and so I have a spatial geodesic going from A to B. So if there is a focusing point in between, it means that this geodesic is not the shortest distance from A to B. There's another curve which is shorter than this geodesic here. Okay. So it's a very similar argument to this that leads you to this statement here. And this tells you that, well, since that is the event horizon, so nothing here can be causally connected to something outside. So therefore, this is not possible. Okay, so there's a little bit more detail here, but this is all the essence of the argument. Did that help?
Indrila, do you have any further questions, comments? Yes, she says.
Okay, very good. So the important point is that this proof is not sort of quasi-local, right? So it's not that you show in this proof that, well, there is some stuff falling into the black hole and that makes the black hole area increase. It is instead concerning itself with something that could happen in the future and possibly in the very, very far future, right? So this focusing point could happen, you know, let's say millions of years later, and still this has an effect on the theorem you want to prove right now, okay? So it's an example of, again, what happens with event horizons all the time. In other words, it is a teleological thing, which means that it knows about things that will happen in the future. So this is just an example of that statement, right? And it should be clear that event horizons have this feature because let's go back to the definition of an event horizon. So it says, event horizon says, well, it's a part of space-time from which no signal can reach the outside world, right? But and you could have a signal that, let's say, stays close to the event horizon for millions of years, and only later you do find out that it is, well, in fact, outside the event horizon, right? So to find out whether a signal is outside or inside the event horizon for all future times, you might have to wait a very, very long time. And this is essentially what is happening in this proof of the area increase law, this classic proof by Stephen Hawking. Okay. So this is not fully satisfactory, right? So in fact, I mean, the proof is of course correct. And this, you can generalize these proofs to include sort of strange effects at the event horizon, not even strange, but in fact, things that happen all the time. The event horizon is not a differentiable surface. It can have kinks, and you can include that and make it all mathematically rigorous. And the same essence of the argument goes through. But nevertheless, the point is that the proof is not a local proof. It concerns itself again with something that could possibly happen in the very, very far future. Okay. So there are sort of more satisfactory interpretations of this. So one very nice example is due to, again, Stephen Hawking and Jim Hartle, that is from 1972. So what they showed was that in a perturbed situation, so imagine that now you have a black hole that is, could be a Schwarzschild black hole, which has a very small perturbation due to some external fields or some stuff falling into the black hole. But it has to be a perturbation, it should be a small change in the geometry of the black hole, okay? So in this case, you can show that in fact, the rate of change of the area of the horizon, of the event horizon, is proportional. There's some prefactors here, and also have additional terms of your matter fields. So that's connected to the shear of the infalling radiation. Okay, well, the shear of the generators of the horizon, that is caused by stuff falling into the black hole. So if there's nothing that falls into a black hole, then the shear vanishes, in fact, and this is true for a Schwarzschild black hole. But if there is stuff, then in fact the shear is non-zero, and that is what gives you the area increase of the event horizon. Okay. So in this formulation, this is local or quasi-local, so it depends on an area, not on just each point. So this tells you that, well, at any given time, the rate of increase of the area is connected to the shear of the null generators. And in this case, there is no reference to anything in the future. Okay? But the price to pay is that this relation derived by Hartle and Hawking, this only holds in perturbative cases. And in fact, hidden inside the calculation is a condition at infinity, which says that, well, everything at infinity at very late times should go back to sort of the equilibrium case. Okay, so this is sort of built into this calculation. So in fact, I'll argue that there can be no such general physical area increase law for event horizons in exact GR. So if you might imagine that, well, Hartle-Hawking showed this for the event horizon in this perturbative situation, is it possible that this can be generalized? And is it possible, in fact, that you could derive such a law for general black holes, right? And maybe it's true, right? You don't, at this moment, you don't know. But I'll argue now that, in fact, there cannot be such a general physical area increase law for event horizons. Okay. So how do we show that? So I'll show it by an example. Okay, that's maybe the simplest way to do this. So let's generalize the Schwarzschild spacetime to what is known as the Vaidya spacetime. And in this case, you have to start off with the Schwarzschild solution written in this case, we'll do it ingoing and in finger sign coordinates. So this is the metric here. So if this m were to be a constant, then this is just the Schwarzschild solution. Okay. But now you take m to be a function of the retarded time of v, and then you say that, and then m is not a constant. In fact, m dot is the rate of change of m, and you can just calculate what the stress energy tensor should be, and that turns out to be given by this expression here. So m dot upon 4 pi r square, so that you can think of the luminosity of the infalling of the infalling matter, and that is what gives you the stress energy tensor in this case. Okay? So it's a very nice generalization of the static Schwarzschild solution to a time-dependent solution. Okay? So let's assume that we have a function m of v, and let's say that m dot has to be always be positive, or could be zero, of course, but cannot be negative, and we'll say that at the limit when v goes to infinity, m of v is finite. So this represents collapse of spherically symmetric infalling dust to make a black hole. Okay. So let's sort of visualize the space-time and see how it looks like. Right. So this is the simplest case. We take a function m of v such that it is 0 up to a point when v is equal to v naught. It increases up to a point when v equal to v1, and then again it becomes a constant after that. Okay. So this means, in fact, that this portion of the space-time, which is the part of space-time for v less than v naught, it's exactly Minkowski space-time, right? Because at that point, m is just 0. So if you go back here and you just set m to 0, then this is just Minkowski space-time written in these coordinates. Okay. And then you have this portion where you have an increasing values of m, and after v equal to v1, where m is non-zero but a constant, then that's a Schwarzschild space-time here. Okay. And in the middle, you have the portion in which the black hole is growing. So now you can ask yourself, well, where is the event horizon here? So you have, in this case, this is then future null infinity to this surface here, and you can just trace the last light ray back, and you can easily see that the light rays, in fact, extend into the flat portion of your space-time. Okay. So there's the event horizon, which extends back into the past, and it enters into the flat portion of your space-time. So in this portion, there is no radiation, right? It's exactly Minkowski space. Any observer here, no matter how clever how sensitive detectors they have, they can never ever measure anything unusual here because this is just Minkowski space. What they do not know here is that sometime in the future, starting at v equal to v naught, there will be this collapse of this infalling dust, which will make a black hole. So observers here can in fact never communicate to observers here. But still, at this point, they don't know it. Because as far as curvature is concerned, as far as any other measurements they might do, there is no distinction here to Minkowski space. Okay? So in this portion, in fact, if you look at again the Hartle-Hawking formula, which contains the shear of the null norm of the generators of the event horizon, and in fact, in this portion, it's spherically symmetric. So in fact, sigma square is exactly 0. So if you were to generalize this to include matter field, there's extra terms connecting the flux of matter fields, but that is also 0, in fact, in this portion of the spacetime. Okay. So I've given you now an example in which there's an event horizon which grows in flat space where there possibly cannot be any radiation that is infalling, there's no matter fields, nothing. So this shows you that in fact that an expression of this kind for event horizons is not possible in general. You can have it in this situation. This is in fact very useful for other reasons. But if you want a general expression for how a black hole area increases, you cannot have an expression like this. So again, this is an important point. So is this clear? So if you have any questions here, please ask.
Students, are there any questions at this stage? Raise your hands or ask your. Yeah, there are a couple of questions. Shubhadeep, unmute and speak.
Hello, am I audible?
Yes, you are.
Yes.
So I have a question. So when we are talking about this mass function, which is a function of v, and it evolves in a particular way from v0 to v1. Okay. So at that point, how do we select what kind of mass functions are physical? Like, do we have to impose a restriction that if you go to the next slide, that how that r equals to 2mv curve goes, that should always lie behind the event horizon?
So in fact, so that's a good question. In fact, there's much more detail in the Vaidya spacetime than I've indicated here. So there are conditions on how fast the mass function can grow, but if you satisfy that condition, everything is allowed. Okay? So you can easily imagine a smooth increase from 0 to some constant value. Imagine a 10 hyperbolic function. So it will be completely smooth. There is no, I mean, all derivatives are defined. And, you know, within that restriction, everything is fine. For any of these choices, if you look at, I was going to talk about this next, which is this, what you might call as the event horizon in Schwarzschild, right? Which is the r equal to 2m surface, that will always lie behind the event horizon in this case.
So we can cook up some kind of mass function where this thing is violated, that it can happen that the r equals to 2m surface, that is the apparent horizon, that lies outside the event horizon. So is that
no, it will, even in that case, will not lie outside. It will still lie inside. So in fact, you can calculate that this surface is a null surface, while this r equal to 2m surface is a space-like surface, in this case, as it turns out. So these two surfaces, yeah, so this has to be always be inside the event horizon. That part I think is fine.
Yes,
There can be naked singularities in this space-time, depending on how fast the mass function changes. But again, within that restriction, you don't have an issue.
Okay, thank you.
Thank you, Shubhadeep. Estuti, can you unmute and speak?
Oh, yeah. Am I audible?
Yes, you are.
Right. So I didn't really get the part where you said that the event horizon, it extends to the Minkowski spacetime. And if I'm not mistaken, I think you said that the observer on one side of the event horizon will not be able to communicate with the person on this side in a Minkowski spacetime. Like I'm not being able to wrap my head around it.
Right. So this is, well, this is again, let's forget about the black hole part here. Right? Just focus on the Minkowski portion here, right?
Right.
So observers, imagine observers now who are moving just at a fixed location and just moving in time, right? So those will be curves which look like this, right?
Right.
And it just means that observers at this time, who are, let's say, here, will receive signals from observer inside only at a later time, right? This is just the propagation of light. There's nothing unusual about it, right? So if you see a signal from an observer near the sun, you would only get it 8 minutes later, right? You cannot get it now. So that's all this is. So an observer here at this time outside this event horizon compared to an observer inside it, this person cannot get a signal from this guy here unless he waits a bit and enters this portion.
Oh, okay. Okay.
So that is only, there is nothing unusual. So there's nothing fancy with black holes, horizon, nothing. It's simply propagation of light at a finite speed.
Okay. Thank you.
Thank you, Estuti.
So
There's a question in the chat which asked, in a dynamical situation of two black holes colliding, can the area law be violated?
no, so it cannot be. So at least not classically. So we'll discuss subtleties about this in the next lecture, but no. So at least in classical physics, unless you have any quantum effects, in classical physics, no. It doesn't matter you have 2 black holes, 10 black holes, 20 black holes, 100 black holes, area will always increase.
There are no further questions at this stage.
Okay. And I should say that this is a nice exercise for you, right? So pick, maybe I didn't make tutorials, but this is a nice thing that you can do yourself. So just cook up a mass function, even take a linear change if you like, in this duration, but you can easily do a smooth function and integrate the equation for the null geodesic and find the location of the event horizon and show that it extends in fact to the flat portion of space-time. Okay? So it's a nice project if you want to spend a couple of days writing a little numerical code for doing this, or you can do it analytically for certain simple mass functions. Actually, it'll require more work analytically, so you might do it numerically, but still, to demonstrate explicitly that in fact, you do have an event horizon that extends from the black hole portion to the flat part of space-time. Okay, so this you can actually show in this example quite easily. Okay, so this should already give you some pause, right? So this should say that, well, event horizons, they are nice. I mean, again, you show all of these beautiful theorems of the event horizons, but it does have this feature. So this is simply a fact of event horizon that you cannot escape. So let me give just one more example here. So you can sort of make more complicated situations in which you have, again, flat space-time up to V0. Then you have an infalling mass function up to V1. And again, a constant mass function between V1 and V2. And then again, you have some infalling mass between V2 and let's say, I'll call this V3. And then it becomes a constant. Okay. So then what's happening here? You have shells of matter that are collapsing. So up to this point, you have again Minkowski space. In this pink portion, you have Schwarzschild with a particular mass, and that's the value of the mass that you get at up to time V1. So this is a Schwarzschild spacetime with a given mass. But again, sometime later, there's more mass that falls in. So the mass increases. And in fact, any person in this observer in this region here, right? You might even observe the collapsing mass if you are somewhere here. And you might say, oh, the mass is not finished collapsing. And fortunately, I'm outside the event horizon, so I can go back to my planet and I can tell them what I saw. But that observer does not know that a little bit later, there's going to be more mass collapsing. And in fact, there will be an event horizon that is outside the observer, possibly, and the observer is trapped. He cannot go outside here. But as long as the observer is here and he looks at this surface here, he cannot distinguish that from any other event horizon, right? So that observer has no way to know at this time that something else will happen in the future that will cause the event horizon to be in fact outside where he is. Okay. So again, this example illustrates that event horizons are very global in nature. And for various reasons, it would be nice to find a replacement for event horizon that does not have this feature. And you might think that I can look at this surface R equal to 2m. So it's very suggestive, right? So you can say, this is what, if this were Schwarzschild, then this R equal to 2m is what I might think of as a suitable horizon in a way I'll describe in a minute. And this is the thing that grows as matter falls in. And that stops growing when matter does not fall. And again, continues to grow as then the matter falls in later, right? So if I look at the surface R equal to 2m in this case, that has a very strange behavior, but it tracks exactly how it tracks exactly the infalling mass, right? So you might think this is a nice replacement possibly for event horizons, which has a strange feature that it actually grows in this portion of spacetime. So again, there's opinions can differ on this, right? So you might say, well, no, what you really care about is the causal structure of the full spacetime. You don't really care about things happening locally. There might be something interesting, but what you really care about is the full global structure of your spacetime, and that is true. So for that, you need the event horizon. Right? If that's what you want to understand, then you need that. But there are more important physical questions than just that global causal structure. For example, you might want to know, how does the mass of black hole increase as the matter falls in? And in fact, for questions of that sort, you need a surface like this. Okay. So again, it depends on what problem you want to address. And for different problems, you might find it more useful to use one of the two different concepts. Okay. So in the rest of these lectures, what I'll talk about is a replacement for the event horizon for different purposes, which uses surfaces like this R equal to 2m surface. Okay. And in fact, surfaces like this one here. So imagine now this surface here. So this is what might be the event horizon. So if an observer is here, then this null surface would have all the properties of a horizon, right? So in fact, it is a horizon for a Schwarzschild black hole. If nothing else were to fall in, then this would be the event horizon. So you might imagine that, well, there should be some special features of this event, of this surface here, which mimic what happens for an event horizon. And in fact, that is true. But it's not to say that this has to be an event horizon, but that requires this extra global condition that needs to know about the full evolution of space-time up to infinity all the way. Okay. So again, just to say that there's different situations where you might not want to deal with event horizons because they're not useful, and you might want to find a replacement for this, which is more local in nature. Okay, so I mentioned all of these wonderful results in black hole physics. So there's one result though, which does not use event horizons.
Badri, I have a nice question. This is Sriram here.
Sorry, go ahead.
The last part is not singular. Is that correct? I mean, there is a piece, which is in the future light cone, which doesn't join the singularity. Isn't that a concern? Or maybe I'm not understanding.
That's a good question. So in fact, this is not complete, right? I was drawing further space-time as the observer here might think it is. But in fact, the singularity will extend till here, and this is not complete. So this will go further on. So it's a good point.
Okay, thank you.
That's correct. Okay, so there is, however, one result which is of great importance in black hole physics, which does not use event horizons directly. And this is the Singularity Theorem. So instead, what is important here is the presence of what is called a closed trap surface. So I will explain that in a minute. And this was first defined and used in this theorem by Penrose in 1965. And this paper also introduced the notion of trap surfaces. Okay? This was subsequently generalized by Penrose and Hawking in further singularity theorems. And in fact, these trap surfaces are the key to understanding black holes quasi-locally. So let me define that now. So let S be a closed space-like spherical surface. So this could be, imagine even a sphere normally in Minkowski space. And for any such sphere, you can define null normals to it. So you can, at any point on its surface, you can, so the null cone can be, you can choose two null rays, so L and N, which can be ingoing and outgoing, okay? So of course there's a null cone, and by combination of this, you can get other null directions, but there are the ingoing and outgoing null directions that are orthogonal to S. So that is unique, okay? So you can scale L by a function and you can scale N by another function if you preserve, again, that they're future directed. So that's completely fine as well. So if you have a trap surface, the condition is that both expansions of L and N must both be negative. Okay? And this you have to realize is a very strange condition. So if you have a normal sphere in flat space, the outgoing light rays will be expanding and the ingoing ones will be converging. Okay? So of course you can think of spheres which are very highly deformed, in which case this is not true. But let's say, imagine now exact spherically symmetric spheres, right? In that case, you can believe that the outgoing light rays will be expanding because they are all orthogonal to the surface and the surface is convex. So the outgoing light rays are diverging and the ingoing ones are converging, right? And the statement is that even for a spherically symmetric surface inside a black hole, it is not true that the outgoing light rays are expanding. Both of them are converging. So which means that both expansions are negative. So if I go back now to the Schwarzschild spacetime, so imagine a sphere here, which is in this diagram is just a point. So, and I have the null normals L and N. So both expansions of L and of N are negative. It means that this sphere is a trap surface. While if I take a sphere that is outside, so the L will have a positive expansion and the N will have a negative expansion. Okay. So, and the separation between these two sets of trap surfaces is given by the event horizon. At the event horizon, the outgoing expansion exactly is 0. Okay. So this surface has a very strange feature, which is that it's a null surface, but it is an expansion-free null surface. And there's one more point, which is that you might interpret this as saying that, well, the black hole has such a strong gravitational field that, well, both light rays have to be converging. Okay, so this is often said, and I confess I've also said this in colloquially in lectures I've given, but it's not true. So the black hole could be extremely large, right? Think of make M as large as you want. The larger M becomes, the smaller does the curvature at this space-time point become. Okay? So the curvature goes as M upon R cubed or 1 upon M square. And if you just fix R equal to 2M, the curvature at any point here goes like 1 upon M square. So if you make M very, very large in the limit, this is almost like flat space. But nevertheless, once you're inside the event horizon, or once you're inside the surface, both expansions are negative. And once you're outside, both expansions are, well, outgoing expansion is positive, ingoing one is negative. Okay. So if you wish in this way, this existence of these trap surfaces is a non-perturbative feature in GR. So it's not something that goes away when you have a very large black hole and small curvature. So in that case, it's not that the gravitational field is very strong at this point here. In fact, it's quite weak. For these large black holes, again, assuming that there's no quantum effects, there's no firewalls, nothing, at least in pure classical GR, if you were to fall inside such a black hole, you would never notice anything. It's only for the small black holes in which if you do cross the event horizon, then you'll have tidal forces. So the force on your head will be different from the force on your feet. That'll stretch you out like spaghetti. So that you'll feel that effect definitely. But if the black hole is very, very large, then that effect is small and you'll cross the event horizon and you'll feel nothing. Okay. But still, once you're inside the event horizon, once you cross the surface, it is a fact that you do have trap surfaces here and you do not have them here. And the separation between these two regions is given by this surface here, which is, in this sense, it has zero expansion in the outgoing direction. Okay. Is this clear? So any questions at this point?
Are there any questions? Please raise your hand or leave a message in the chat. There are no questions at this stage.
Okay, very good. So let's go back here. So as I was saying, so it's a signature of black holes, the existence of trap surfaces and again, it's important, every part of the definition is important, right? It has to be a closed trap surface. So you can have, if you, let's say you drop the condition of it being closed, so then you can have a plane. So a plane can have zero expansion, right? So that is completely fine. I mean, plane but so it's important that the surface has to close at some point. So the condition refers to the entire surface, not at any one point of the surface. That's why it's not a local definition. It's called a quasi-local definition, something in between a local and a global thing. So it does require the surface close eventually, but still it does not require that, it's not a fully global condition, right? So you can, in principle, you have a chance of verifying whether a surface is trapped or not. Right. So what is important for us is what is called a marginal trap surface. So this is separation between a trapped and an untrapped surface. So we say that this expansion has to be zero. And if you wish, for mathematical reasons, you might impose this condition that the other expansion has to be negative, but that's not always true. So you could have a surface that is highly deformed. So you could have imagine a black hole that is highly deformed because of the presence of another black hole nearby. So in that case, it is possible, in fact, that this theta n may not be negative. So there might be portions on the horizon where theta n is positive, but still that's not important. The important point is this condition here, which is the theta of L, which is the outgoing null normal, has to have zero expansion. Okay. So there's other things here which I don't need to mention right now. We'll do that later when we come to numerical relativity. But at the moment, this is the important point, which is that a marginal trap surface must have, is a closed surface, which is spherical in topology, and it has one expansion 0, and that is the outgoing expansion, and one expansion negative, that is the ingoing expansion. Okay. So now you might say, well, can we use it to define an event horizon in a different way? Can we use it to say that the separation, that the surface that separates trapped and untrapped surfaces, that is the event horizon? So that wouldn't be, well, we don't know yet, but that may not be a global definition. And that may lead to a useful definition of an event horizon. Is that true? And in fact, this is an open line of research, in fact, in GR, if you wish, if you're interested in this topic. So there is a conjecture by Doug Eardley back in '97, which is very nice paper for its time, definitely. So it's a very influential paper, I think. So that conjectured, in fact, that the event horizon is the boundary of the space-time region containing the trap surfaces. So how does this apply to the Vaidya space-time, right? So we can discuss that in a minute. So again, I will not discuss this in too much detail here. I just want to emphasize the complexity of the problem here, okay? So you saw that the spherically symmetric trap surfaces, in fact, in this case, only extend up to here. So in fact, just like in Schwarzschild, this surface here is the boundary of the trap surfaces. This portion here does not contain spherically symmetric trap surfaces. Any trap surface, any point here is a sphere which is untrapped and is inside the event horizon. Okay. However, the problem is that there exist non-spherically symmetric trap surfaces that extend outside this R equal to 2m surface. So in this case, it's not a question of angular momentum or other fancy issues. It's simply the fact that the family of trap surfaces is a complicated family, right? So the spherically symmetric ones are the simple ones, and those extend just up to here, and those do not extend up to the event horizon. But there do exist non-spherically symmetric trap surfaces which extend almost all the way to the event horizon. And to make it even more complex, right? So remember, trap surfaces have zero expansion in the outgoing direction. But the event horizon has positive expansion in the outgoing direction because it's growing at this point, right? So the expansion of the null normal of the event horizon is positive. So in fact, a marginal trap surface cannot extend exactly to the event horizon. It cannot touch the event horizon in a smooth way. Because if it did, then its null normal has to have positive expansion, while for a marginal trap surface, it must have zero expansion by definition, right? So this tells you that the limit of trap surfaces as they extend to the event horizon is a singular limit. So it's a very strange, it's a mathematically very involved situation here, and this is not fully understood. So there's examples in Vadya is understood, I would say, at this point. So I won't discuss that in detail here, but the general case is completely open. Okay. So, but at least as far as for the spherically symmetric trap surfaces go, everything is nice. So things up, so the R equal to 2m surface, it seems to be a nice surface. So it contains all the spherically symmetric trap surfaces. Outside it, it is untrapped, and it approaches the event horizon at late times, and it responds to the infalling mass, exactly the way that we expected. Okay. So again, any questions at this point?
Students, if you have questions, please raise your hand. None I can see. Nothing. Ah, there is one. Near the horizon of a very massive black hole is weak. Then how does the event horizon work?
Well, it works. Again, this is something that you have to wrap your heads around, right? Event horizon is not necessarily a signature of strong gravity. It's a causal feature of space-time, right? It's not to say that there's nothing strange happening in the space-time. Of course, you don't have event horizons in Minkowski space. But it does not mean that curvature is large. So that is simply a fact, right?
But then there is a conflict to say it is Minkowskian at that point.
Well, I mean, why is it? So look, locally, you can always have a coordinate system locally, which is Minkowski-like, right? So you could always do that, even at the Schwarzschild spacetime, right? Just take a point on the event horizon, make a little patch of Minkowski in which you have.
Understood.
So it's like making your Christoffel connection vanish at that point, right?
Understood.
You can do that at a point.
Understood.
And it's only that approximation is, it has a regime of validity, right? So it's going to how large that portion of space-time will be. If you're in a very highly curved part of space-time, then that portion of space-time in which you can make it to be flat locally is a very, very small portion. While if gravity is weak, then that's a larger region of space-time.
I understand. There was a hand raised, I noticed. Sumit, would you wish to speak? Just give me a minute. I will unmute you. Yes, please unmute and speak.
Yeah, am I audible, sir?
You are.
Okay, sir. I mean, what is this benefit of spherical closed two-dimensional cross section? And I mean, I couldn't follow like why beyond r equals to 2m there is a non-spherical closed topology. I mean, how do you deduce that from this Vedya spacetime?
Well, it's not a trivial. It is spherical in topology, right? So I should distinguish between spherical and topology. So any sphere that is deformed highly is still topologically a sphere. So it is still topologically a sphere, but it's a highly distorted sphere. So it is a complex calculation. It's not something that I'm going to present here. I hadn't planned to present it here. So maybe I can do it if it's an involved topic. So it's not a trivial thing. So you're right to ask the question. So I'm just stating it as a fact, and I can provide the references if you want to look it up. But it is a fact that you can, in this spacetime, there do exist non-spherically symmetric margin trap surfaces that extend outside this R equal to 2m surface. Okay?
So thank you.
It is simply a fact, and you can prove it, but it's not something that is easy for me to do here without further background.
Yeah, I mean, is the assumption of just a closed cross section sufficient, or like why are we assuming this spherical closed topology? I mean,
because that is what is appearing in the singularity theorem. That is the starting point for this line of analysis, right? So you say that in the singularity theorems, what is important is a closed trap surface. It does not mean it's a trap surface that is exactly spherical. It could be highly distorted. But as long as you have a closed trap surface, and it has to be closed, having an unclosed trap surface is no, it is not unusual. The fact that it is closed and it is trapped, that is what leads to singularity.
Okay, thank you.
Thanks, Sumit. There is another question from Oindrila. She asks, why the space-time is spherically symmetric and spherically symmetric trap surfaces lie within R equal to 2m. Is there any reason why spherically symmetric trap surfaces should be more important than non-spherically symmetric trap surfaces? What happens in a rotating space-time?
Right. So in this case, so in general, you're completely right. So in general, of course, space-time, if you have rotation, it will not be spherically symmetric. So, but you might imagine that the surfaces that you want should share the symmetry of the space-time, right? So in that case, in the rotating space-time, you might imagine, well, maybe axisymmetric trap surfaces are important. So, but in general, you're completely right. So it is not to say that the other surfaces, trap surfaces, are not important. So they're all important and you have to understand them, but it's only that if you imagine there's a preferred geometrical surface, it should share the symmetries of your space-time in general, right? So if you want to have any special surface in Badri, then you would expect that surface to be spherically symmetric. But it is true that there is no reason apart from that to sort of, prefer spherically symmetric ones to ones that are, let's say, slightly non-spherically symmetric or highly non-symmetric. So that's possible and they exist and it's a fact.
Thank you, Badri. There are no further questions at this stage.
Okay, so now let me now construct what is called a dynamical horizon. So this is, the idea here is that you start off with a marginal trap surface and you evolve it in time, okay? Once you do that, then you get something that is a topology of S2. For each cross-section is spherical and you have time, so it's S2 cross R. So, and this surface and the study of such a surface is what will occupy us for the rest of these lectures, okay? So it seems like a very simple structure, right? So you have these marginal trap surfaces that evolve in time and you stack them up and you get a smooth surface by combining them all, okay? And this surface can have different properties in different situations. So if I go back to Schwarzschild, so if I look at the event horizon here, that is exactly of this kind. So each cross section is a sphere and it's a marginal trap surface. And the combination and the union of all of them gives you the event horizon. So it has topology of S2 cross R. So that is true here. And it has the condition that the expansion of the null normals is 0. Okay. So this is, in this case, a dynamical horizon in this definition. Similarly, if I go back now to Vaidya, so if I look at this surface here, so you can calculate, in fact, and this could be another tutorial problem, which is that calculate the expansion of the outgoing null normals in Vaidya and show that at R equal to 2m, the expansion vanishes. So each of these cross sections of this surface here is, in fact, a marginal trap surface. So this combination of all of them, which gives you this surface here, is a dynamical horizon. In this case, it's not a null surface, it's a space-like surface. And that's one more thing that you could prove. Okay, so it's very, very different than, let's say, in this case, if I look at the R equal to 2m surface here and combine them with the surfaces here and then combine them with here, the whole thing is a dynamical horizon. It is space-like in this portion, it's null in this portion, again space-like, and again null. Okay, so this is what is sort of implied by this picture here. So this is meant to capture this essential feature of this surface, which is that it is a 3 surface of topology S2 cross R, which is foliated by marginally trapped surfaces. Okay. So now, again, as I said here, you do have, in fact, non-spherically symmetric trap surfaces here. Okay. And if they evolve smoothly in time, you can combine them to get non-spherically symmetric dynamical horizons in the space-time. There is one unique dynamical horizon that is spherically symmetric, and that is this one here. But there exist other such horizons which are not spherically symmetric and which are different from this one. Okay, but this one is the one that is most useful for any calculation that you might want to do here. Okay. So let's make some terminology now. So there's different kinds of dynamical horizons. So you have a space-like dynamical horizon in which you have a space-like signature for the whole surface. So that's a space-like case. The null case is very special. So that is called an isolated horizon. So that is to illustrate the fact that it's isolated in the sense that nothing is infalling into the horizon. So in this case, for example, this portion is an isolated horizon. This portion is a space-like dynamical horizon. That's again space-like. And that's an isolated horizon here. Okay. And again, as we will see in the next lecture, these are not the only two examples. You can have a time-like horizon as well, and you can call it a time-like dynamical horizon. It's also called a time-like membrane in the literature in many places. Then again, you have other things called trapping horizon that I will not discuss here in detail that has additional conditions that you want to impose on these expansions. But again, you have this whole zoo of these horizons based on these different properties of this surface. Okay, but again, the essential thing that you have to consider is a surface which is foliated by these marginally trapped surfaces. Okay. So is that clear? Any confusion on these definitions?
There is one question, just raise hand. Sumit, unmute and speak, please.
Hello, am I audible, sir?
Yes.
Yep.
Okay, yeah, sir, you consider for the Vega spacetime R equals to twice m being the space-like dynamical horizon, right? But for example, if I just consider R equals to twice of m, it's as a function itself, it represents a surface of codimension 1, I guess. So from that, I mean, how do you able to deduce at least quasi-locally that it is just a space-like surface?
Oh, I see. Yeah, so it is the codimension 1. So this is codimension 1. So space-time fully is 4-dimensional, of course. The cross sections are 2-dimensional, and you have time, right? So this is a codimension 1 surface. So that is completely right. So what you have to do is that at each point of this surface, you have to project the space-time metric, find the metric on this codimension 1 surface, that is the intrinsic metric on the surface, and you have to say, is that a Riemannian metric or not? Look at its eigenvalues at each point. If you have all positive eigenvalues, so that's a space-like surface. If you have a null direction, that is a null surface. If you have one negative eigenvalue and two positive ones, that's a Lorentzian surface or a time-like surface.
So the surface ST here is basically the space-like cross-section that you're considering.
Yes, the cross-section is always space-like in this construction. The cross-section is always space-like, but this direction may be time-like, maybe null, or maybe space-like.
Okay, and what sets the time direction over here? Because I mean, this dynamical horizon. I mean, because in the next slide, your Lie derivatives are with respect to. If you can please go to the next slide, I guess.
Yeah.
Yeah. So here in the definition of this trapping horizon, your Lie derivative is with respect to this ingoing null vector. Is it right?
Yeah.
Yeah. So I mean, what sets your time vector? I mean, time evolution vector in this case of dynamical or these cases of horizons.
Again, that's a good question. So you have to make a choice in this setting. So you have to say that you need to choose a future direction, a past direction, an outgoing and an ingoing direction. And these in different situations will be different, but usually there's a natural choice that you make, right?
So they should be like a linear super combination of these ingoing and outgoing null vectors.
Yes, indeed. So you could also do it a different way, which again, I will discuss in the next lectures. You could say the following. You could say that, well, I have a dynamical horizon, and we will see that the area increase is in fact monotonic along these horizons in most situations, not always, again, there's subtle aspects here, but almost the interesting case is the area is monotonic. It increases or it decreases. It cannot be sort of, increase and then decrease. So you could make the claim, you could sort of do it in the following way. You could say that, well, let's use the area to define the direction of time. So that is completely valid in most situations, with again, caveats as I'll mention later. But you could say that I don't need to introduce an extra notion of time. I can just look at this surface. I can look at the foliation by these marginal trap surfaces and look at the area of these cross sections. And I say that, well, increasing area is future in time, decreasing is past in time. You could say that.
Okay, and do we actually require the space-time to have a continuous time orientation as well? I mean, because we are defining these as quasi-local definitions. Like, I mean, there should be a continuous time orientation for the space-time manifold. I mean, do you require that sort of requirement over here for these definitions?
No, so that is, I mean, the other things will go wrong if you cannot do that in a space-time. But at least for the calculations here, which are all quasi-local, it will not be affected. As long as in some local patch, which is large enough, you have a consistent time orientation, then you're fine.
Okay, thank you, sir.
No other questions at this stage.
Okay, very good. So this formalism has, in fact, many applications. I'll talk about some of these in the next lectures. So, in fact, the sort of initial motivation for these studies was, in fact, the black hole entropy calculations. And so I'll talk about black hole mechanics in this formalism. Then there's properties of black holes with hair. There's many applications in numerical relativity. And there's mathematical properties of trap surfaces. So there's a large literature on all of these aspects. And you can find some of these in these review articles, which I realize are quite old. So there has to be a more recent review article, which we're working on. I don't know how far we'll get in the near future, but this should give you at least a good idea of these of this framework. So let me sort of talk about, before I go into details on isolated horizons, let me just mention one aspect of this, which is this time evolution of these marginal trap surfaces. Okay. So you can ask the question, well, I talk about time evolution here, and I want to stack these up in a smooth way, right? What guarantees to me that this will be smooth, that they even exist? Of course, they exist in things like Schwarzschild, but in general, is there any reason to believe that the evolution of these things has to be smooth? So then the question concretely in mathematical terms is that, let's say that I have in this space-time, I start off with a Cauchy surface that is space-like. And so that is so I slice my space-time up into Cauchy surfaces. So that defines for me the different time slices. And at each time, I find a marginal trap surface, right? This I can do numerically, I can do in different ways as I wish, but in some way or the other, I find these marginal trap surfaces. What tells me that the evolution of this has to be smooth if I start off with one of these cases? So in fact, now I'll discuss this mathematical result, which in fact shows that generically this evolution will be smooth. And the condition that you need, and this was shown by these people here back in 2005. So the condition is that, in fact, at each time, if your marginal trap surface is stable in a way I'll define in a minute, then this evolution has to be smooth. Then this world tube has to exist, and therefore the dynamical horizon has to exist. Okay? And the condition is the following. So if I start off with, this is now meant to represent one Cauchy surface at any given time, in which I found a marginal trap surface, and that is this red surface here. Okay? So if at this time, I can deform it outwards and make it, and it becomes untrapped. So these little arrows are meant to illustrate deformations of this surface to get this dashed blue surface here. If I deform it outwards, then I should be untrapped. If I deform it slightly inwards, it should become trapped. Okay. If this is the case, then in fact, the time evolution of this red surface has to be smooth, and you do get a smooth dynamical horizon in this case. Okay. So if I go back to the Vadya case, and let's imagine this case, Imagine now slicing this up at different time slices, okay? So imagine now different time slices. Of course, you have to complicate, some of these slices might intersect this twice, but just look at the outer intersection, okay? Then that intersection, on that intersection, right, if you deform that marginal trap surface outwards, it becomes untrapped. That you can show again is true here for the spherical symmetric ones. So therefore, again, in that case, this proof applies, and you do get a smooth evolution here and a smooth dynamical horizon. Okay, so it's a very important mathematical result. So this sort of tells you that the construction I made here, which is this smooth tube of these marginal trap surfaces, it is true, it does exist generically. And in fact, numerically, you always find that it evolves smoothly, and there's almost no case I know where there's any doubt about the sort of an unsmooth behavior. It's not that you can have a marginal surface appear at one time and disappear for no reason. That doesn't happen. And you do have this smooth evolution, and therefore it is interesting to study the smooth surfaces of codimension 1 like I've defined here. Okay. So this is the an important mathematical result. Again, I won't go into the proof of this, but still this is good to know. Okay. And let me not spend time on this, and let me go to sort of the thing I want to do today, which I realize is now quite over time. So we'll continue this next time, but I'll introduce this in the last 15 minutes. So before this, so it's a change of topic now. So I'm going to talk about isolated horizon. So this is the case in which I have a null dynamical horizon. So that is the situation in which I have a black hole, which is itself isolated, but the rest of the space-time can be fully dynamical. Okay. So this is meant to illustrate sort of portions of space-time like this. Okay. So this could be a small portion, could be a large portion. I mean, and the rest of space-time could have radiation. There could be radiation going in this direction, very, very close to the event horizon, or very, very close to this isolated horizon, but nothing is infalling. That is the condition here. So the area is a constant. Okay, so this is a beautiful example of a thing that I want to talk about. So before I do that, any questions at this point?
Students, any questions? Please raise your hand. Sumit, unmute and speak, please.
Yeah, sir, like you said that this dynamical horizons are intersected by Cauchy slices, right? Is it correct in that sense?
Yeah.
So, like, what initial data do you prescribe for this Cauchy, for these Cauchy surfaces? Do they extend all over time? These are just T equals to constant surfaces, and you just prescribe the corresponding induced metric and extrinsic curvature, or you're considering only the two-dimensional cross sections and prescribe their corresponding initial data for the evolution?
No. So it is what you said. It is the three-dimensional against the Cauchy surface of codimension 1 again. So you prescribe metric and extrinsic curvature, and then you find where on this surface you have marginally trapped surfaces.
Okay.
So you can do this again in Badri, you can do this in Schwarzschild, you can do this, and I'll discuss it again in the next lectures. In the numerical relativity setting, you do have the starting point is initial data in which you prescribe the metric and extrinsic curvature, and you numerically you find where these marginally trapped surfaces are. They call apparent horizon. That's it. So then the statement is that these evolve smoothly if these marginal surfaces are stable in the sense that I just described.
Okay. Thank you, sir.
Any further questions? There are none for now.
Okay, so let's continue. So what I'll do now is to introduce a bunch of definitions which are increasingly more and more stronger conditions, and I will demonstrate how the laws of black hole mechanics work in this setting. Okay. And what we want to do is to extract the minimum amount of information that is required to talk about a black hole that is isolated in a space-time that itself is dynamical, okay? So this is an excellent approximation for almost every situation that you can think of in nature, except for, let's say, a black hole collision in the very late times when the two black holes are close to each other. Apart from these situations, this is an excellent approximation, okay? So our goal is not to now start with very strong conditions, it's to say that, well, let's think of the weakest conditions that we can impose and still get useful results from it. Okay, so that is sort of the goal. and we'll make this condition more and more stronger, and then we'll see how different results are derived in the different cases. Okay. So let's start. So the simplest definition is what is called a non-expanding horizon. Okay, so this is the sort of the basic definition that you need in the study of isolated horizons. So we have to start with the null surface, which is codimension 1. So in a space-time of 4 dimensions, it is 3-dimensional. So we'll call that surface delta. So that is said to be a non-expanding horizon if, first, it has topology S2 cross R. So it must have cross-sections that are complete, and it must have a sort of a R direction that is meant to be time. And the other thing is that it has to have these null generators. In other words, to make it a bit more formal, you can say, well, let's look at this projection, which takes us from S cross R to S2, which is just the usual projection, right? So take any point in the sphere, take any point in R. I project it by saying I drop the R, and that gives me projection. So this way, this projection gives me a sphere, and there's a metric on the sphere that is completely Riemann and completely normal. And then the other condition is that for any point X in S2, the inverse of that is a curve, which is along the R direction, and we require that this curve has to be a null curve. Okay, so it's a null surface topology of S2 cross R, which has these null generators on it. The second condition is that the expansion of this null surface has to vanish. So if I take any null normal to the surface, which is along these curves, right? So I've said that if I take the inverse projection of any X here, that should be a null curve. So that will, from that I can have a null vector tangent to it. I can scale it as a like. I can take F times L to be a completely valid null vector as well. But the expansion of all of these has to vanish. Okay. So if I scale this L by any function F, which is not 0 and which is always positive, then even for that L, the expansion has to vanish. Okay. So that's the second condition. And that is, again, we'll need all of this condition in what I'm going to talk about. The third condition is that for doing physics on these surfaces, let's assume that the Einstein field equations hold at delta, and that matter fields satisfy the energy condition that I'll describe here. So the weakest one that you need is the following. You need that this quantity here, which is the contraction of TAB with LB, the negative sign, that has to be future and causal if L is a future null normal. Okay, so we'll discuss all of these in detail in the next slides, but these are the three conditions that I need. So any questions on these conditions? Because I'll assume these and then go ahead and derive the consequences, but I need you to understand what these conditions are. So any questions or any confusion on these conditions?
Students, questions, please. Badri, can I ask, what does it mean to say future causal? What is expected of this vector?
So it means it's future directed. So that is, you need sort of a time orientation, at least on the horizon here.
Okay.
And secondly, you need it, causal just means it's not space-like.
Okay.
So it means that this vector is not space-like, right? So it means that this vector is in fact future, and it is either time-like or it is null.
Okay, thank you. Yeah, there is Sumit having another question. Please go ahead, Sumit.
Am I audible, sir?
Yes, you are.
Oh, okay, thank you. If you can just clear my understanding of this construction. So you have this basically this X, the point X lying on the the S2 surface, and then you have the inverse projection as X as being the null generators, right? Of the null hypersurface. But if you once you start with a closed S2 surface and then you generate these null generators, does that by anyhow let you construct a hypersurface orthogonal null hypersurface, or this hypersurface orthogonality does not need to be imposed via this construction?
Yeah, so that in fact was my next going to be the first point I would make. So in fact, yes. So once you have in this construction, this L that you get will be hypersurface orthogonal.
Okay.
by definition, right? So if I take the L that I get from this construction, which is then tangent to these curves, so that is tangent to the surface. So that means that I can integrate these null curves, if you like, and stack and combine them to get a smooth surface. So that is equivalent to saying that this is surface orthogonal.
Okay. Okay. Thank you, sir.
Okay.
Are there any further questions? There are none at this stage, Badri.
Okay, good. So it's important to understand this condition. So, and again, if any confusion comes in the next steps, then please stop and ask me exactly then, okay? So this is meant to be the minimum that we should ask of a black hole horizon in equilibrium, okay? So that is the goal of this first definition that I've given you. But this simple notion, in fact, leads to non-trivial results, as we'll go through a few here. So the first is that, again, I won't prove all of these, so I hope that I give you enough understanding that you can prove this with some work. So the first thing is that any complete cross-section of the horizon has the same area. Okay. So this, first of all, so again, this is a strange result, right? If we imagine a cylinder, let's say take cross-section to be just a circle, and just take one more direction, just consider a cylinder, okay? And take a cross-section of this cylinder. So I can make the cross-section to have any length as I like. Or if this were a space-like surface, S2 cross R, the whole thing were space-like, if I take a different cross-section, I can make the area of the cross-section to be as large as I like, just by deforming it arbitrarily, right? It's only in this null case, when it is expansion-free, that this area will be a constant. And this might seem like it seems like in Schwarzschild might seem like a trivial thing. So, but it is in fact, it takes some work to prove it, right? So it means that if in Schwarzschild, if you take any cross section of the horizon, so in the, let's say the Eddington sign con is the standard thing is to take V equal to constant. But I could take V to be some function of theta and phi and still get a closed sphere, right? And this cross section could be highly distorted, but still its area is guaranteed to be the same as the undistorted one. Okay, so that means that there's a quantity called the area, which is sort of a unique thing for a given isolated horizon, for a given non-expanding horizon. Okay?
There is a request to repeat the first condition in the previous slide.
Oh, the first condition here?
Yeah.
Okay, so the first, let me state a bit differently. Maybe it might help if I don't talk about projection, which might confuse some people. So what you need is a surface which is three-dimensional, so codimension 1. Topology of S2 cross R, so it has spherical cross sections, and one cross section is, let's say, time. And it must have some preferred curves which are null, which are tangent to the surface. So you can say that this surface has to be ruled by these null curves. Does that help? Is there a different way to phrase the same thing?
There was a message on, yeah, says okay.
Okay. So, okay, so that is the first thing. Now, the second thing is the following. It's a little bit technical thing, but it is a surprising result. So first of all of you are used to the, so given a metric, all of you know that there's a unique connection associated to a metric, right? So that is the Levi-Civita, the Christoffel symbols, right, for a given metric. So now, in a null surface, so if you have a null surface, so you do have the metric on the null surface that is inherits from the space-time, right? So I can always project the metric and get the metric on a null surface that is completely natural. The metric is degenerate, so it has one null direction. So one eigenvalue is 0, the others are positive, right? That's the condition here. So in this case, as it turns out, it is not true that the metric determines fully what the connection is. So if we go to the proof of what the expression is for the Christoffel symbol in terms of the metric, I mean, all of you have seen that in a GR course. If you repeat that for a metric that is degenerate, which has a null direction, it is not true that the connection is uniquely defined by the metric. Okay, So intrinsically speaking, just given the metric is not enough. That metric does not determine the connection on that surface. It does have a connection that it inherits from the space-time. So I take the space-time connection, which is the covariant derivative here, and I project that onto the null surface. And the question is that a natural connection on it? And the answer is that it is only if I satisfy the expansion equal to 0 condition. Otherwise not. Otherwise there is ambiguity. Okay. So this gives an intrinsic connection, which I'll call D of A when restricted to delta. In other words, I take the space-time covariant derivative. I project this index always tangent to the horizon. So I take a pullback of this connection, if you like. So this gives me an intrinsic connection dA only for a non-expanding horizon, only when this 0 expansion condition is satisfied. Okay. So if you like, a non-expanding horizon is nice in this case, which is that the space-time connection does give you a consistent connection on the horizon itself, which in fact is not determined by the metric. So it's a different part of the free data on this horizon. So this is simply a fact here, okay? So this is something that you can, with some thought, you can derive for yourself. So it's now 11, so I'll stop here. So in fact, think about this last part and we'll continue from here tomorrow. So we can end up with questions. So any questions then we can take now?
Yeah, thank you, Badri. Are there any questions, students? Please raise your hand or you can type out your question in the chat.
Well, let me ask first. I mean, did people understand the lecture? So, I mean, I don't want this to be very complicated and to go over your heads. Was it too easy? Was it okay? Was it too difficult? I think some feedback would be useful here.
Can you kindly respond in the chat or you can speak up as well? Students, can you kindly respond and say whether you are happy? I mean, you could follow a good fraction of the lectures. There is one yes.
Okay, good.
Yeah, there are a few yeses. Okay, I can't see any no.
Okay, no would be, yeah, if no, then that's good to know. Okay, but people ask questions. I'm happy to stay longer. So any questions?
Okay, yeah, there is a request to see whether some can be illustrated on the blackboard. Yeah.
Yeah, so I could use this blackboard. Did it? Yeah, so in the next lecture, I could illustrate this on the blackboard if you wish. I mean, that's why there's limitations of Zoom in this way, right? So
Yes.
in person is always nicer. Unfortunately, we can't do that right now, but we can try on the blackboard next time, yes.
Sure. Paolo Pani was giving the lecture on the blackboard, but others were using the slides. So yes, you may just need to turn it so that, oh, I noticed there are other questions about slides being available. I guess we can request you for the slides and make them available on the website.
Absolutely, yes. I'll do one, yeah.
Yeah, there is a comment which says that the part about isolated horizons and NEH was very new. Why are we interested in NEH?
So the reason is because this will lead us to strong, first of all, we'll see interesting results already for a NEH. And with a slight additional condition, we'll do the laws of black hole mechanics here. So we'll do zeroth law and the first law. And this is what is used in numerical simulations as well. So this will lead us to definitions of the black hole, let's say the mass, the angular momentum, higher multiple moments, everything follows from these definitions.
Okay, are there any further comments / questions? I don't see any hands. Oh, there is one hand raised. Just bear with me. Yeah, Sumit. Go ahead, Sumit.
Hello, am I audible, sir?
Yes, you are.
Okay, thank you. Sir, I have a question regarding the teleological property of the horizons that you mentioned in the beginning. So I might be wrong, so please just correct me. So I mean, we have, I mean, in the membrane paradigm, analogy, we have that the uh, event horizon behaves like basically a fluid, probably given by the Damon-Navier-Stokes equation. So in that, we have the bulk viscosity turning out to be negative. I mean, I have found a few, reasons for this bulk viscosity turning out to be negative that was probably given by Professor Padmanabhan, I guess, and he attributes the negative bulk viscosity of the horizon as being attributed to this teleological property of the event horizon. I would like to know your take on this, thing. If
Yeah, so
I'm
this was already yeah. So in fact, maybe Eric might have talked about this, right? He's a real expert on this topic. But yes, so as you said, already when Damur did this calculation, it was the case that this strange sign of these quantities in this membrane paradigm that is connected to the strange property of the event horizon. That's true.
The thing is that, do the perturbations of the horizon, these perturbations are defined by this Damon-Navier-Stokes equation, if I am correct. Like, so all these are basically partial differential equations, and partial differential equations should be, I guess, local partial differential equations. So, but the equations that you write on the horizon, for example, the Null-Raychaudhuri equation or the Damon-Navier-Stokes equation, these are local partial differential equations. So, uh, but as you explained, this black hole in its own nature is entirely global. I mean, one should know the complete information of the black hole, event horizon beforehand. So
Yeah,
do these, okay, yes, sir.
yeah, so the way that this happens is the boundary condition of this differential equation. Okay, so the teleological nature appears always when you have to give the condition as connected to the endpoint of this evolution. So normally what you do when you solve an equation, right? You say at any given time, at initial time, I have, let's say you solve Newton's equations, right? So you prescribe the position velocity at initial time and you evolve that future in time. So that is what you do normally in differential equations. For event horizon, what you end up doing inevitably is that you have to give a condition at the end. You have to say that the condition is solved such that at the end it has to satisfy such and such condition.
Okay, okay,
So it's not an initial condition, it's an sort of like an end condition, and that is where the teleological nature comes in.
okay, okay. Thank you, sir.
Thank you,
And that's
Sumit.
what I mentioned when you go back again to this Hartle-Hawking calculation for the area increase for an event horizon. So in fact, that is what they also do. So the condition there is imposed at the end of the at t equal to infinity.
Okay, okay. Thank
So
you, sir.
as a solution to a differential equation, it's completely fine. I mean, so there's nothing wrong with it. But it does have this strange feature that you have to know about the future behavior to understand what is happening now.
Thank you, Badri. There is a question which asks, can you please give an idea about how dynamical horizons differ from trapping horizons? In what situations are they different?
Yeah, so that's, yeah, it's a bit of a technical question. So there are, so I would say, I think it's not useful to sort of look at the distinction between these here. So in almost all the physical cases, this is true, okay? So again, it's not always true, but again, generically these are true. So it's not, I think, a physically interesting distinction between these things for at least the application that we have in mind. So you can construct examples in which this is not, the two things are different. But so far, I think they have not turned out to be useful examples. So one thing, for example, is that this condition itself, the theta n being negative, right? So that is always required on a trapping horizon. But that, as we shall see, in fact, that might be, in fact, the one condition that is not that important. So as we shall see in practice, that when you have binary black holes, so black holes merging, and you look at these dynamical horizon in these situations, you do not satisfy this condition always. So there's in fact important cases in which this is not true. Even for isolated horizons, and imagine if you have a black hole which is surrounded by matter fields which distort the black hole. So in that case, you do have many situations where theta n can be positive. So perhaps I think this condition is the one that is sort of the least useful of the trapping horizon ones. But once you have that, then this appears naturally, this other condition.
Thank you, Badri. I don't see any further questions. Thank you very much for your lecture. Thank you, students, for joining.